This is problem 61 from chapter 15. In problem 61, the 15 kilogram block A slides on the surface for which the coefficient of kinetic friction is 0.3. The block has a velocity of 10 meters per second when it is 4 meters from the 10 kilogram block B. If the unstretched spring has a stiffness 1,000 newtons per meter, determine the maximum compression of the spring due to the collision. Take the coefficient of restitution to be 0.6. So I've drawn the diagram here. In the diagram in the book, they call this distance S, but remember you want to be careful if you call this distance S because this S is not the same S as what you have in your formula for the elastic potential energy. So be careful of that. So we want to find the maximum compression of the spring, and I chose 4 different events to look at. So initially we have block A traveling at 10 meters per second. When block A touches block B, the collision is going to begin. At the moment that the blocks first touch, B is still at rest. When the collision ends, B is now moving. And then finally, we're looking for when the spring is at its maximum compression. So first, I'm going to look between event 1 and event 2. So this is from event 1 to event 2. And at event 2, block B is still at rest because this is when the collision first begins. Now, what they gave me was the distance between block A and block B. So if they're giving me a distance here, rather than using the impulse-momentum relationship, I'm going to use the work-energy relationship because impulse has time in it here, but work has distance in it. So I don't know anything about the time, but I do know what the distance is. So I'm going to use the work-energy relationship. So I have the initial kinetic energy plus the initial potential energy plus the work done by forces other than the force of gravity and the force of the spring is equal to the final kinetic energy plus the final elastic potential energy. Well, at event 2, B is still at rest, so the spring is still at its rest length because the spring was initially unstretched, and the blocks are moving on the horizontal surface, so the height is not changing. So I have no change in gravitational potential energy and no elastic potential energy. And block B is at rest to begin with. At event 2, block B is still at rest, so the kinetic energy I have is just from block A. So kinetic energy, remember, is 1/2 mv squared, so this is 1/2 times the mass of block A. Its initial velocity is 10, so that's 10 squared. Final kinetic energy is 1/2 times 15. This is only coming from block A, so that's VA2 squared. I do have work done in this problem because I have a coefficient of kinetic friction, so I'm going to have on block A a force of kinetic friction acting to the right. The velocity is acting in the other direction, so for the work, I have the dot product, so I'm going to get something negative for the dot product. So this is minus FKF times delta R. The distance is 4. And for the force of kinetic friction, if I look at the forces acting in the vertical direction, I have the normal force acting upward. I have the force of gravity for block A acting downward. Those are my only forces in the vertical direction. So the force of kinetic friction is the coefficient of kinetic friction times the mass of the block, which is 15 times 9.81. So that's my force of kinetic friction. So I have 0.3 times 15 times 9.81 for my force of kinetic friction times 4 for the distance between block A and block B. So I have a 15 in each term. I can cancel that out. And this is 100 divided by 2, which is 50, minus this is 0.3 times 9.81 times 4, so that's 11.772. And this is just 1/2 times VA2 squared. I can solve this for VA2 by multiplying both sides by 2 and then taking the square root. So this is plus or minus 2 times 50 minus 11.772. Now, the block was going to the left to begin with. When it touches block B, it's still going to the left. So I want the negative sign here. And I get VA2, which is the velocity of block A when it first touches block B before block B begins to move. And that is negative 8.744 meters per second. So that was going from event 1 to event 2. Now I'm going to go from event 2 to event 3. This is for the collision. I'm going to use the impulse momentum relationship for the collision. And before, just block A is moving and block B is at rest. So that's the mass of block A times the velocity of block A when the collision first begins. The velocity of block B is 0. So the momentum of block B is 0, plus the impulse. Now, if you look at the forces acting on the two blocks during the collision, you have the normal forces between the two objects, which are equal in magnitude and opposite in direction. So if you look at block A and B together, the impulse from the normal forces will be 0. You also have a force of kinetic friction going this way. And you have, if block B begins to move, then the spring will be compressed, and then you'll have a force of the spring. Now, take a look in your book at page 254. They tell you on page 254, if the time period over which the motion is studied is very short, some of the external impulses may be neglected or considered approximately equal to 0. So this is called the impulse approximation. We're going to use the impulse approximation to ignore the impulse from the force of kinetic friction and from the spring. We can say if the collision took place over a time period which was equal to 0, then the net impulse would be equal to 0 because dt, well, when you integrate, you'd get delta t, which is equal to 0. So it no longer becomes an approximation if delta t is equal to 0. And we're going to take care of the force of the spring and the force of kinetic friction after we figure out what the velocity of B is. So we're using the impulse approximation here. And so we have an impulse of 0. The only forces we are considering are the forces between A and B. And by Newton's third law, that gives us 0 for the net impulse. And afterwards, we have the momentum of block A and the momentum of block B. Along with the conservation of momentum, we also know what the coefficient of restitution is. So we're going to use this and our impulse momentum relationship. So we have E is equal to 0.6. By equation 1511, we can write down this is equal to the difference in the final velocities, where here my final velocities are VA3 and VB3. And if we put VB3 first in the numerator, then it comes second in the denominator. So in the denominator, it's the difference of the initial velocities, which is VA2 minus VB2, but VB2 is equal to 0. And I know VA2 and it's negative, so I have to put in negative 8.744. While I do this, I'm also going to multiply both sides by VA2, so I have 0.6 times minus 8.744, and that is minus 5.246 for VB3 minus VA3. From my equation here, I can put in the mass for block A, which is 15, the velocity, which is negative 8.744, plus 0 is equal to 15 times VA3 plus the mass of block B is 10 times VB3. So now I have an equation here and an equation here, and I can solve those two, and I get VA3 is equal to positive 3.148. So now block A is going in the other direction. Block B is going in the negative direction with a speed of 8.394. So using conservation of momentum, we were able to find the velocity of block A and block B when the collision ends. Now block B is moving. Now we're going to go from event 3 to event 4 to find the maximum compression of the spring. So we're going to use the work-energy relationship for that. We know the potential energy for the spring is 1/2 kS squared. Now at this point we should be considering the force of the spring and the force of friction, but in your book they do not include the force of friction after the collision, and since they don't include it in the book, I'm not going to include it here. So we can pretend that the floor that B is on from here to here has no friction. So we're going to pretend this part of the floor has no friction, which is going to give us in the answer in the back of the book. Okay, so we just have the force of the spring. The force of the spring, we're using the elastic potential energy for that. So we have T1 plus V1 plus the work done by forces other than the spring and the force of gravity, which is 0 because we are ignoring friction, is equal to T2 plus V2. But since I am going from event 3 to event 4, I should make this a 3, and this a 3, and this a 4, and this a 4. And we're just looking at block B. So this is 1/2 the mass of block B times VB3 squared plus, if the spring didn't compress at all when the collision ended, which would be true if the collision takes place over a time interval which is 0, then the elastic potential energy is 0 here. And then we have the final kinetic energy, and if the spring is at maximum compression, this would be where the block turns around. So when block B turns around, the velocity is 0, so we have 0 for the kinetic energy, plus for the elastic potential energy we have 1/2 K times S squared. Let's call that S4, and that's what we are looking for. So now hopefully we can just plug numbers in and find our answer. So the 1/2s cancel out. The mass of block B is 10. The velocity, I'm squaring it so it doesn't matter that it's negative, and I have 8.394 squared is equal to K. K is 1,000. So this is 1,000 times S4 squared. So S4, which is what I'm looking for, is 10 times 8.394 squared divided by 1,000, and then take the square root. And that gives us 0.8394 meters, and that is the maximum compression of the spring. So that concludes problem 61.